Hi, I'm Griselda Chavez and join me in this race. This work is motivated to give an answer to the angular momentum problem, or the apparent loss of angular momentum during gravitational contraction of molecular clouds. This problem in observations looks like this, where the specific angular momentum goes as the radius to the 1.5. To answer this question, we analyze an SPA simulation of giant molecular clouds undergoing global hierarchical collapse, where we define fixed Lagrangian set of particles that we also track in time, from the past and to the future. As a first result, our numerical sample reproduces the observed slot with remarkable accuracy in the JR plot. Regarding the tracking of sets from the past, 5 in this case, we find that the interactions with neighboring particles is essential to recover the observed slope. Finally, in tracking sets to the future, we see how part of the material in the periphery lowers its density, taking away angular momentum in a similar way to what happens in an accretion disk. The fraction of this lost material ranges from 5 to 60% approximately. We conclude that the JR relation arises from a global tendency towards gravitational contraction mediated by angular momentum loss via turbulence viscosity, and also losing part of the clone material, which could put a limit to the star formation efficiency. Thanks.
Hi, I'm Andrea Bonilla from the University of Mexico, and I would like to present my poster. It has been thought for years that molecular clouds are turbulent, but there are many works, included Lee Harman works, where it's argued that molecular clouds should be collapsing. So, what is happening in reality? Well, one way to distinguish this issue could be to look at the actual velocity dispersion of stars. So, if we have a cloud that is collapsing, then its star should exhibit a constant velocity dispersion just because it's a violent relaxation process. Instead, in a turbulent cloud, massive cores within the cloud should have higher velocity dispersion just because they are produced by stronger shocks. And so massive stars in there should also have higher velocity dispersion. This is the idea. And what we found is that indeed, in simulation of global collapse, stars have a nearly constant velocity dispersion, while in simulation with turbulence, high mass stars have higher velocity dispersion than low mass stars. Then we went to look at the ONC. And of course, I would love to tell you the results in Orion, but I prefer to pick your interest, so you will visit my poster. Thank you.
I am Nadmit Sakre, doctor student at Hokkaido University in Japan. Today I will present my poster on a paper titled Massive Core/Star Formation Triggered by Cloud-Cloud Collision, Effect of Magnetic Field. Massive stars are important in astrophysics. However, their formation process is not well understood. Cloud-cloud collision is a strong candidate for massive star formation. We studied the effect of magnetic field on massive dense core formation in colliding unequal molecular clouds by performing MHD simulation with sub-parsec resolution that can resolve dense molecular cores. We show that greater number of massive gravitationally bound cores are formed in strong magnetic field 4 microG models than weak magnetic field 0.1 microG models. This is partly because strong magnetic field suppresses the spatial shifts of the shock layer that should be caused by nonlinear thin shell instability. The spatial shifts promote the formation of low mass dense cores in weak magnetic field models. The strong magnetic field also support low mass dense cores against gravitational collapse. In strong magnetic field, perpendicular and oblique to collision axis models, we found that massive bound cores are formed in filaments which are roughly normal to magnetic field. Thank you.
Hello everyone, I'm Stefano Berrezzo and I'm a PhD student at University of Cologne. In my work, I consider hydrodynamical and magneto-hydrodynamical simulated molecular clouds within the Silk Zoom project, with and without stellar feedback. I produced and analyzed 12CO120, 13CO120, and C2 synthetic emission maps. The chemistry of this simulation is based on the Nelson and Langer 97 chemical network, to which I added a novel post-processing routine to account for the second ionization of carbon due to the stellar feedback. Here in the top right of the slide, you can see an example of these emission maps for one selected snapshot of a hydrocloud. And on the bottom left, you can see, for example, of expanding bubble in the C2 maps, and you can observe how the simulation can reproduce not only the bubbles themselves, but also some smaller scale structure, like, for example, the pillars. An interesting result is that we find a positive correlation between the ratio of CO and C2 integrated and stacked intensity with the molecular hydrogen mass fraction. Anyway, there is a scatter of a factor of a few among different clouds and line of sights, and because of that, it's difficult to use this line ratio as a reliable measure of the H2 mass fraction. Also, we claim that assuming chemical equilibrium yields to a significant underestimation for C2 or overestimation for CO of the total luminosity, up to more than 30%. Regarding C2, this is due not only to the underestimation of the C+ abundance itself, but also to the underestimation of the collisional patterns of C+. Thank you.
Hello, everyone. My name is Matthew DiFiore, and I'm a fifth-year PhD candidate at the University of Michigan working with Michael Meyer. I'd like to introduce you to my most recent work, currently submitted and under peer review, investigating the binary formation of very low-mass stars and brown dwarfs in the Orion Nebula cluster. In the first paper in this series, we created a double PSF fitting algorithm to search for binaries using empirical PSFs designed specifically for the Advanced Camera for Surveys on the Hubble Space Telescope. In the work presented here, we use the same algorithm to identify binary systems, while at the same time applying a more rigorous examination of the outputs from our code, as well as a more rigorous analysis of the completeness and reliability of our method. This approach increased our spatial resolution by about 50%, which is below the diffraction limit of HST, and allowed us to recover companions down to the background limit, which is about 1 magnitude fainter than previously accomplished. Our sample consists of 75 very low-mass star and brown dwarf primaries found in 4 broadband filters on ACS. We identified 7 candidate companions and observed a binary frequency of 12% over physical separations of 23 to 230 AU and mass ratios of 0.5 to 1. We can conclude that this binary population within the ONC is distinct from the galactic field population, with the probability of the field frequency being the true ONC frequency of 10 to the minus 6. Dynamical interactions of the lowest binding energy binaries over the next few million years, given the current density of the ONC, is a possible mechanism to sculpt its binary population to resemble that of the field. Please consult my poster for more details on this project, and feel free to email me with any questions. Thank you.
Binarity is intrinsically linked to the formation and early evolution of massive stars, and currently it is thought that up to 100% of them harbour at least one companion. To gain a better insight into binarity, we need to study these stars at the earliest possible stage, and massive young stellar objects, or MYSOs, represent a key origin point in the lifetime of massive stars. Our research targets MYSOs across the whole sky as we aim to investigate their binarity statistics and mass ratios using the UKITS and VISTA infrared imaging surveys. We use statistical methods to determine the probability of a nearby object being a physical companion of the primary MYSO. And we also used multicolour information from UKITS and VISTA to estimate the mass ratios of the companions. Work is ongoing, but the estimated multiplicity fraction ranges from 32 to 45% for the sample at typical MYSO separations between 1,000 and 20,000 AU, agreeing with the previous MYSO survey when comparing like for like. Also, a significant fraction of the companions appear to have mass ratios greater than 0.5, indicating a disagreement with the binary capture scenario. Future work will involve ex-shooter spectroscopy to probe closer separations and find companions that cannot be resolved through imaging.
Hello everyone. OB association in Cygnus have been studied for decades, yet only Cygnus OB2 has been analyzed with enough detail. In this paper, we revisit the OB association in Cygnus. The historical OB association are displayed in figure 1 in galactic coordinates with associated Poincare motions. we find that only Cygnus OB2 and OB3 stand out as real associations. So we decided to explore again this region and determine physical parameter of a carefully selected sample of sources using an LCD fitting process. And then with a new flexible clustering method, we found 6 new groups that are displayed in figure 2. And then we analyzed these groups by calculating exact physical and kinematic properties. We notably found some expansion, especially in the galactic longitude direction, helping us to trace their origin. We also found 2 large-scale kinematic patterns with a length of about 160 parsec and a velocity of 25 km per second, displayed in figure 3. Such a correlation between galactic longitude and proper motion in galactic longitude can have several causes, but our main hypothesis is the feedback of a previous generation of stars. If you want to know more, you can look at my poster or even read the paper.
Hello everyone, my name's Sam Pearson. I'm a PhD student at the University of St Andrews. I'd like to introduce you to my poster, which covers my work on young brown dwarfs in NGC 2264. For this cluster, I've constructed a catalogue of brown dwarf candidates and also followed up a subsection of these candidates spectroscopically using KMOS on the VLT. The key takeaways from this work is that you can significantly increase the efficiency of your follow-up spectroscopy if, when selecting brown dwarf candidates, you require them to show additional indications of youth. We've confirmed the first brown dwarfs in this cluster, and we find that the majority of the brown dwarfs we've found are really very young. We'd expect them to be less than 500,000 years old. We also, using our confirmation rate and the list of candidates that we have, we'd expect there to be about 400 brown dwarfs in this cluster between 20 and 80 Jupiter masses. And we find that the substellar mass function for this mass range is well approximated by a power law with a slope of about 0.4. For any more information about any of this or details of any of the methods, please come and have a look at the poster.
Hi, I am Ignat Tagliati, and I am presenting our preliminary work on a comparative study of these fractions. It is accepted that planets should form in less than 10 million years, and this time scale is based on the observed decline of the fraction of stars with disks, as inferred from surveys of young clusters at different ages. However, it was suggested that these fractions could be underestimated. And the reason is that most previous surveys were focused on narrow regions of around 2 parsecs from the center of the clusters. Given that the young cluster can span, we would be probing only the stars that were closer to the centers, which in principle should have smaller disk lifetimes due to interactions with nearby stars. And this is actually the hypothesis that we want to test. We aim to know whether our disk fraction estimates depend on the spatial scale considered or not. This is an example of what we are doing applied to the young cluster NGC 1333. We first identify members from new Gaia data using a tool called Clusterix, and we do this considering 2 different fields of view, compact and extended. You can see the size of the fields in the central figure, where the red circle corresponds to a radius of 2 parsecs and the blue circle to 20 parsecs. After the members are identified, we finally apply a color diagram to estimate the disk fractions associated to each field of view. We aim to do this for a statistically significant number of clusters representing different physical conditions, with the goal of comparing the disk fractions obtained from the 2 different fields of view. Our preliminary result, based on the 10 clusters that we have analyzed so far, is in the poster. So if you are interested, please have a look. Thank you.
Hello everyone, I'm Priya Hasan, and I talk about my poster on membership in star clusters using machine learning. Now, star clusters are the building blocks of galaxies and the key to understanding the formation and evolution of stars and galaxies. But the biggest problem about star clusters is their membership study. And therefore what we did is we took up a sample of about 9 clusters, which we studied using the Gaia data. What we used as our training set was a membership sample which was already provided by Cantat-Gordon 2018 paper, and we used that as a training set for our sample. We used random forest to actually get a larger membership database compared to what was originally there. And what you can see in our plots is these orange dots are the training set, the blue ones are the new dots. So you can see we've considerably increased the size of our clusters. We have enhanced the color magnitude diagrams, which you can see it over here, the yellow being the old and the blue being the new. And here you can see the parallax data as to how well it does things. it fits. So you can see that in conclusion, by using random forest, we've increased our sample of membership, and we've got a lot of substructure also, which we've discovered in these clusters. And what you can actually have a look is this very paper, which has been published in the European Physical Journal, and you can get more details over there. So thanks a lot.
Hi, my name is Claire Davis. I'm a postdoc at the University of Exeter, and this is my poster on SEDBIES, a Python-based spectral energy distribution builder for young stars. My poster outlines the motivation for making SEDBIES and its benefits to the star formation community. Most importantly, SEDBIES dramatically speeds up the compilation and inspection of archival photometry and the subsequent building of SEDs. It combines an automated interface with Vizier using AstroQuery, together with a distributed database of catalogs, tables, and other reported measurements which have not been digitized or are otherwise excluded from Vizier. I provide two example cases in the form of Herbig star MWC 297 and the transitional disk HD 143006, highlighting the benefit of using SEDBIES over Vizier's photometry viewer, particularly when you're interested in retrieving longer wavelength data. The poster PDF is fully hyperlinked to take you to the code paper, the code repository, and to short video demos on YouTube. SEDBIES is also equipped with tools to expand the database. So if you notice that a particular source of photometry or flux measurements is missing, see the paper or get in touch with me for details of how to add it to the database. Finally, the ease at which SEDBIES can be installed and its compatibility with Mac, Linux, and Windows operating systems makes it a useful tool for undergraduate labs and research projects.